So yeah, this is technically a talk on space mining. So I would be remiss if I did not say those words. But if you, it's kind of funny if you use ChatGPT or one of these other AI language models, and just go type in, show me what space mining looks like in 2026. And if you're like me, you'll probably get this graphic of an asteroid with 100 tons of infrastructure, looking very sci-fi, but using traditional methods. And, I don't think that's happening in 2026. Actually, if you do 2020, I think you get the same graphic. So something's broken there. But so space mining is certainly something we're looking at, but it feels more in the future, right? And something that we're working towards. But what I want to talk to you guys about today is something that we're doing right now. And it is more or less similar to what we might call space mining, but we refer to it as ISRU, so in situ resource utilization. Some of you may be familiar with that concept. I'm guessing NASA coined it, so Honeybee actually is building some of the first generation robotic systems that are typically planetary sampling applications, sample acquisition, but really a lot of the fundamental capabilities that we're working on improving are very aligned with ISRU and eventually this concept of space mining. So in situ resource utilization, it sounds really fancy. What it really means is we want to live off the land. So we want to harness those local resources. And what do we mean by local resources? We're not trying to get platinum from near-Earth asteroids. We're talking about how do we create sustainability on the moon, on Mars, and these sort of immediate goals that that seems like NASA, but across the world, this is the goal right now, right? And so, what are those resources? So, water is sort of the obvious one, right? And typically in the form of water ice. So if you can get water, you now have propellant, you have life support, you potentially have construction materials, right? So water is sort of the obvious one, but there are others. So atmospheric gases, not as relevant on the moon, but on Mars you have CO2 that you can capture. Volatiles in the subsurface, so potentially accessing those as well to extract, again, maybe CO2, nitrogen, and other gases that can be useful. Metals, so the regolith on the moon particularly has lots of potential for extracting metals from that. And then you can use the regolith itself as a construction material, right? You can use it to block radiation. You can even use regolith as a thermal battery, which is something that Honeybee is looking at as well. And so when we talk about ISRU, very similar to mining, we sort of have these three phases of that pipeline, right? So resource prospecting sort of being the first step of that, okay? So when you talk about resource prospecting, that just means what are the resources and where are they? If anyone's familiar with NASA's Viper mission, and if you've been following it, it's been a roller coaster ride. The rover, including, in fact, fun fact, this is a Honeybee drill right in the middle. It's built, it's tested, it's ready to fly. What wasn't ready was the lander to get it there, right? So it didn't have its ride to the moon, unfortunately. And NASA said it was canceled indefinitely. So a lot of us were very disappointed to hear that. A lot of effort went into trying to revive that. And sure enough, we kind of went full circle. And Honeybee's parent company, Blue Origin, now is actually the launch provider and the delivery vehicle to get Viper to the moon. So we're really excited about that. But I just want to highlight, Viper is sort of a perfect example of how we're going to prospect for resources on the moon. Second is going to be the acquisition of those resources. And this is where Honeybee really shines, because one of our sort of main specialties is robotic systems for collecting samples. And we've done this for decades now, and I'm going to talk a little more about that. And I'm not going to spoil it because I have slides on each of these two technologies here, but this is essentially once we know where those resources are, how do we get them? Typically from the ground, right? Out of the ground. And then lastly, how do we actually process those resources? So less of a honeybee focus, but still extremely critical, right? What do you actually do with those? And so my example that I'm showing here, so the idea here was to say we're either really close to doing it or we're actually already doing it, right? And of course, smaller scale than that ChatGPT graphic, right? But resource processing actually was just demonstrated on Mars with MOXIE. So we're already taking CO2 from the Martian atmosphere and collecting that as a potential resource. This was very small on the order of grams, right? So very, very small demonstration, but it is happening, and it'll continue to improve. So why our ISRU, right? To some it may seem obvious, maybe not. The current model is we launch things to space, we use them, and then we're done with it, right? And this has worked okay. That's kind of all we needed for what our objectives have been in space. But as we continue to discuss sustainability, to actually put boots on the ground to stay there, and to then transition to Mars and do similar, that model doesn't work. So I have very specific numbers here. I mean, if you look at this 1 to 65, this is sort of the lower bound of if you plug numbers into the rocket equation, it's that. But really, it's even worse. So there's something that we call an ISRU gear ratio. So your gear ratio is how many kilograms does it cost you to get that 1 kilogram to your destination. And so more practically speaking, you're probably looking at 100 to 1 gear ratio when you have to send propellant, a reserve propellant that gets you off one of these surfaces, or particularly the moon, and worse for Mars. So if you're looking at, I think right now, see anywhere between 2,000 to maybe 20,000 dollars per kilogram to get something to space. Multiply that by a factor of 100. I mean, this is not sustainable, right? No pun intended, because you want to be sustainable, and in order to do that, you have to find a way beyond that, right? So with that mass penalty in mind, there's really no way around. If you want the sustainability, you have to eventually create this. And even SpaceX, who has ambitions of $100 per kilogram, even they're talking about ISRU. So this is something that absolutely will happen, and it already is. And again, speaking towards why we need it, right? I think I already touched on some of these. If we're putting astronauts there, obviously crew life support is #1 priority. Also priority to help them leave, right? So you need that propellant. And then some other things that may be less thought about, but critical, like, do you need a launch pad? So you need construction materials, right? And then, agriculture, something you probably want to have eventually as well, so you have food on the moon, Mars, wherever you are. All right, so I'm going to step back and talk about honeybee real quick. So honeybee's actually almost a 40-year-old or over 40-year-old company. We were a small company for a very long time. Initially, I won't get too much into it, but I'll say we built a robotic bartender in the early days. And then sort of got our big break in space when we developed the rock abrasion tool for the MER rovers. So that's that tool on the end of Spirit and Opportunity that you see. It's more or less a grinding wheel. So that tool was used to touch the Martian surface, touch rocks, grind away that top layer to expose, a fresh layer, and then you kind of flip your instrument around. You have, I believe, a imaging suite, a spectrometer that could then do certain science, right? 2008, we were if you know about the Phoenix lander, Honeybee built a scoop on that. So it wasn't just a scoop. On the back side of the scoop, you had what's called a rasp. So it was a little tiny drill. You could essentially break up that material so that you can create a loose granular material, and then you could scoop that up and bring it to an instrument. So kind of our early, kind of see where mining is coming into play here, right? And then more has followed. So sample manipulation system on Curiosity. So that was the carousel that would, once you collect a sample, you have to manipulate that sample, put it in front of an instrument. So, and also March 2020, and always kind of working with JPL. So actually, JPL's drill on March 2020 had a lot of inspiration from past honeybee designs, including, I believe, a honeybee patent was actually utilized for that drill bit. So the company was acquired by Blue Origin in 2022. So we're not technically a small business, but Honeybee proper is about 400 employees spread out across 2 offices. So we have an office in Los Angeles area, California, and that's our exploration systems division. That's the one that I represent. We also have an office in Longmont, Colorado. So that's going to be more of the component sort of spacecraft building blocks. So actuators, gimbaling systems, slip rings, and things of that nature. So let me move on here. All right. So the first technology I want to kind of highlight along the lines of this, sample acquisition, space mining idea is going to be Lister. So if some of you may be familiar, the next slide will show you a little bit about why this was recently in the spotlight. But this is what we call a gas drill. So the way this works, and this system weighs approximately 10 kilograms. It's not a very heavy system. If you speak pounds, that's about 20 pounds. And the way this works, it's a 6 millimeter tube, steel tube. You can sort of picture a garden hose on a reel, obviously a little stiffer, and it's steel tube. And then you have this mechanism with a BLDC drive, that extracts that tube, straightens it, and advances it downward. So if you're familiar with the concept of coiled tube drill, or oil and gas and mining industry, similar, but just extremely compact version of that. And then we have compressed gas that we bring with us. In this case, it was nitrogen. And then we can release that gas right at the tip, and we use that energy to essentially drill our way downhole. So there's no spinning like a traditional drill would be. And so you can picture the ability to go extremely quickly into the subsurface. And this was particularly critical in this case because this was actually meant for primarily a science objective. So we were measuring the thermal profile of the lunar subsurface. And if you're familiar with doing engineering for the moon, if you put heat out, it's really hard to get rid of on the moon. So you really want to operate very quickly when you're doing this sort of process. So you don't add too much heat because then that affects your thermal measurement that you really want to be sort of the raw lunar conditions. So this was able to excavate up to one meter deep, and I'm going to show you now how we actually did this. So Lister was a payload on Firefly's Blue Ghost 1 mission. And you can see it right here, integrated onto the lander, which is integrated onto the launch vehicle. And you can see the GIF here of what's going on, but I also have a video. Hopefully this works. There we go. All right. So this is Lister operating. This is on the moon. Obviously sped up a bit. There's our space miners. So this is actually our team in the Firefly control room getting to see actual video shortly after the operations. So very exciting. There's a lot here, but I think the message I would kind of like to get here is this is extremely low mass, low power system that was able to excavate not just the diameter is 6 millimeter diameter, but even larger. You can see here at the surface, you're removing a lot of material with pretty low amount of energy. And so systems like this, you can imagine, can be very scalable towards something that can not only perform science downhole, but maybe do something with the regolith, if you can capture that. Speaking of which, we had another payload on this same exact lander, same exact mission. This one was called Lunar Planet Vac. So similar fashion, uses pneumatics, stores gas, very similar subsystem for the pneumatics, but instead sort of a single degree of freedom arm dropped to the surface, entirely passive, So it's almost like an inverted scoop. And instead of a mechanical scoop, you're releasing compressed gas. So there's no atmosphere on the moon, right? There's very, very low atmosphere. So you can't rely on sort of a negative or a suction. Instead, we're introducing the gas. The path of least resistance is what takes that regolith into our sample collection chamber. So you can kind of see the before and after over here. So perfectly clean before, that's good. And then we have our sample after. What's hard to see is there's actually a sieve right there in the middle. So we have a secondary operation where not only are we collecting the regolith, then secondarily we can actually sieve and size sort particles. So this, you can imagine why this may be useful in certain applications. So this was also successful. It was not as much, it was a very lower bound of our goal for sample collection, and the reason being is CLIPS is a very low-cost program where you have to make compromises, and in this case, wherever that cone lands when it reaches the ground, that is where it is. So you're not meant to be perfectly compliant with the surface, but in this case, we were way off nominal. We were about as far off nominal as we had assumed was our worst-case scenario. So the amount of sample we got was, right around 10 grams, a little more. So not quite what you want for a real resource collection operation, but it is a good technology demonstration of where this could potentially lead. Okay, Trident. So Trident's kind of our baby. This is a drill that Honeybee has been working on for quite a while. Not because it took us long to figure it out, because it's been a NASA funded since our SBIR days. This started off, I believe, as a lunar drill, potentially, and then switched to Mars, and then switched back to the moon. And then it got picked up by two programs at the same time, one being Viper, which we already talked about, and then the other being Prime 1. So this is our 1 meter class rotary percussive drill. So it operates with a Z stage, sort of this longer stage here, actually 2 stages, one to deploy the drill to the surface, the other one to actually perform the drilling stage, and then it has a rotary percussive head. So I think most people probably picture the top layer of lunar regolith to be this sort of soft, sandy-like material. If you've played around with the simulants, it's almost like flour, right? That's not representative of everything on the surface of the moon, right? You have clumping effects, you have potentially rocks, you have pretty hard materials that you can encounter. So if you just go there with a rotary drill, it's very likely you could have a bad time. So the percussion is sort of how we de-risk getting stuck. So we can turn that percussion on, just like from Home Depot. You have the rotary percussive drill, everyone knows. That gets the job done a lot better, right? It's exactly what we have here. This one, the drill itself is 20 kilograms, 19. So again, in pounds, probably about 40 pounds, right? Not including the avionics. So it's a separate sort of subsystem on the lander. This is the ConOps, particularly for the Prime 1 mission. So this was, again, a science objective. So one of the neat features about this is we can do what we call bite drilling or bite sampling. So we drill about 10 centimeters, pull that regolith to the surface, and then a mass spectrometer is there to capture, scientific data, right? And if you do that in 10 centimeter bites, you can actually learn the stratigraphy as well. So understanding the layering is a critical input as well, both from a science perspective and from resource. I think I'm a little off pace. So Prime 1 mission, I mentioned, this already happened. If you're familiar, it's the IM-2 lander. It did not stick the landing. Very unfortunate. But the only fortunate part was that we landed on the top side, which you see in the image here. So we were excited about that because we actually got to run our ops. So we drilled the sky. It used to be our motto, mind the sky. So we actually did a full health check, full sort of nominal or baseline operations. They won't call us TRL-9 because we didn't touch the ground, but that's okay. So we were still happy to get something out of that. So we're really excited for Viper. I don't have a slide on Viper, but that's coming up next, 2027. Give us a second chance to see our drill in action. So JAXA has a mission called MMX. If you're familiar, this is going to Mars, Moon, Phobos. This is a sample return mission, which is really cool. So that truly is mining a resource and bringing it back to Earth, right? Honeybee is building the actual sample collection and acquisition system. This is a really small sample. This one is actually integrated into the footpad of the lander, which was actually, fun fact, what PlanetVac was originally meant to be until that got rescoped to the deployment arm you saw. But on Phobos, we're actually on the lander leg. Different gravity profile, much lower gravity. And so this one has been delayed quite a few times. We've delivered hardware, everything's, as far as I'm aware, ready to go. So we're excited maybe for a 2026 launch. Phobos and a few more years to get a sample back. But very similar to PlanetVac, but I think just trying to show sort of the, every environment where you might find some sort of resource that you're interested in is going to be a little different, and that affects the way you go about your design of your systems. And all of those are extremely different than when you do this on Earth. So I don't know if this is the last one, but this one's really exciting. So NASA New Frontiers mission, Dragonfly, this one launching in 2028, I believe. Honeybee's actually responsible for quite a bit. We are not building this awesome rotorcraft. So if you're not familiar, Titan has an atmosphere, but also low gravity. So it was a prime destination to have a flying craft that can kind of hop around and do sampling activities. So this is, again, a science mission, but Honeybee's developing a drilling system, and actually we've already started delivering some hardware. So this is very happening, right? So we built the drilling system that actually, this is a miniaturized rotary percussive drill, similar to Trident that I showed, but much smaller. So that'll drill down on the magnitude of centimeters, bring up a sample, and then we have a similar pneumatic system that draws that sample in. We're responsible for the entire sample acquisition system. We're responsible for the sample carousel, so we can. The objective is to go to multiple sites to sample different regions of Titan. So every time you get a new one, you turn your sample carousel so you have a new sample tube ready for the next one. So we're doing all that. This is a huge endeavor for Honeybee. We're super excited about this. It's been really fun, and we're very excited to see that one launch. All right, Redwater. So this one's close to my heart. I led this project at Honeybee. Fun fact, it's the only R&D one I've shown yet. This has not been funded for a mission. It's about the closest maybe sci-fi I'll show, which is Mars has ice in the mid-latitudes, if you don't know that, or at least we're pretty sure. So it's below quite a bit of overburden. But with that new scientific breakthrough, it really opened up the door for this idea of mining water on Mars. And so as far as I'm aware, we're the first people who've built technology to actually do that, right? So this system is imagined to go on some sort of mobile system, possibly a NASA rover or JPL rover, go to this location and then do something, what's called a Rodwell. So if you're not familiar with a Rodwell, they actually been doing this for a really long time. They did it in Greenland in the 60s. They still do it in Antarctica. Essentially, you drill deep into the ground, and then you melt the ice, and you create this underwater cavity, and then you circulate the warm water to keep your well growing slowly and steady, and then you can extract the water as a usable resource. So for these remote locations where you don't want to be hauling in tons of water constantly, you actually do this essentially in situ, right? ISRU. So we took this concept and we applied it to Mars. And so, until we have a little more concrete data that these subsurface, ice sheets exist, which I think we're getting there. We may not see something like this fly, but we've been developing. You can actually see one of our tests. We tested an earlier system in our vacuum chamber, Mars pressure, Mars temperatures. We also did something that we could actually see in our freezer. So we did an actual Rodwell, just a much smaller scale, red dye, red water, right? So that was really exciting. I was really proud to lead that one. And I think another good example of how, we talk about space mining as an abstract concept for the future, but some of us are really already working on some of the technology that we're going to need to actually do this. All right, this was a honorable mention that I threw in there right at the end. Full disclosure, I'm not an expert on PVEX, but I feel like I'd be remiss if I didn't mention it. So PVEX is very similar to Trident. Now this one, when Trident won, contracts to go to the moon, PVEX was like the runner-up. Okay, so this one is like once you prospect and you find the resources, you want PVEX to follow that. PVEX is a coring drill. So very similar to Trident, but there's a hole in the middle, right? That's how a coring drill works. So instead of bringing all your cuttings to the surface, you're trapping the sample inside of your core. Now, if you put heaters on that, you can heat it, you can extract volatiles, and then you can do quite a few different things there. One of the things you can do is you can send the volatiles straight to a mass spectrometer and do science, right? You can learn about the subsurface. And that would maybe be more of a prospecting mission. But you can also have a cold trap, and you can collect those volatiles. Now, water ice, I think at the high end, maybe you get 3% in PSRs, maybe higher in the PSRs, I can't remember, don't quote me. So this is a very difficult thing we're doing, but it works. I mean, we've proven this. I believe we're calling this TRL 6, and we're confident that this is something that NASA would like to fly in the near future. So for fun, did this video play yet? It did, yeah. So essentially, as we're drilling down and heating, we have I can't remember exactly what we've embedded in this Regulus sample to be our quote volatile, but you can see the Mylar balloon actually filling with that gas as we're drilling. So just sort of a proof of concept for the PVEX technology. That's pretty much time. I threw these up. I'm not trying to sell you, I promise. Chris Sackney is our VP. He's awesome. He comes from mining, and now he's one of the most recognizable names in sort of like the space application of drilling and all this, and he's put out these 3 textbooks. I have all of them. They're fantastic. A lot of them touch on some of our technology and other interesting concepts out there, and I was really, really proud that Redwater made the cut for the cover, so I had to get a copy of that. Yeah, thank you.